here we have a function that is shown on the axes below. Wonderful. So f of x, what does it look like? Is it a straight line? No. Parabola? No. Cubic? Yep. Right, it has that cubic shape, and in this case, since it's going up, down, up, I know it's actually a positive cubic. So positive cubic, as opposed to a negative cubic, which is down, up, down. Cool. So it's something like x cubed, right? A positive cubic. Now the question is asking us to sketch the gradient function on the axis below. So a reminder, the gradient function tells us what the gradient is of the original function. So for example, the gradient in this area is positive, right? It's a steep line going up. So the gradient function will have a positive value. Similarly on this side, our function has a positive gradient, so our gradient function would have a positive value. What about these turning points here, right? The max and the min. The gradient at a turning point is 0. So our gradient function will have a y value of 0. And finally, the section connecting the turning points, it's going downhill. It has a negative gradient. Okay, so how does this help us? Let's go back to what we know about this shape. We know that it is a positive cubic. So if we differentiate it, we would get something like 3x squared, for example, or in other words, a positive quadratic. Right, so it goes from a positive cubic to a positive quadratic. So our gradient function would look like a positive quadratic. But how do we know where to position it? That's our next question. So with that, or rather to do that, we can use the turning points as a place to start. A reminder that at a turning point, the gradient would be equal to 0. So since these axes are on the same scale, just to help, I'd like to put a dashed line all the way through. So do that for both turning points. Right, of course, this is a bit extra, but who doesn't like being extra? So we know that the gradient at the turning points is 0. In other words, on the gradient function, they are x-intercepts. Because, for example, when x equals like 4.5, its gradient, the y value, is 0. So on our original function, when x equals 4.5, the gradient of our original function is 0. Right, it's a turning point. Cool. And now we know our gradient function is a positive parabola. So to connect the dots, right, we connect them with a positive parabola. Something like so. And let's just check that this makes sense. So between the turning points, we expect the gradient to be negative. In other words, on our gradient function, all of these values should have a negative y value. They should be below the x-axis, which they are. And then either sides of the turning point, the gradient is positive, right, the green section. So the y values should be greater than 0, right, above the x-axis. And finally, again, at the turning points, the gradient is 0, so they are the x-intercepts. Alright, so to get achieved on this question, we had to clearly mark the x-intercepts, which we've done, and connect them with a positive parabola. If yours is a little bit different to mine, that's fine, as long as it's a positive parabola. Alright, see you next time. Actually, I'm back. I forgot something. So this question, somehow it's a merit question. Specifically, for the merit point, we had to get the turning point of our quadratic, this point right here, to be in line with the steepest section of the yellow, right? In other words, this point here is the most steep of the yellow section. It's decreasing the most, so our gradient will be the most negative. In other words, the minimum will be approximately in line with x equals 1. And so if we did both the intercepts correctly and the turning point at approximately 1, then that would be merit. Alright, okay, bye for real this time.